In this video, we're going to talk about 3x3 systems of linear equations. Alright, let's start with our definition. A linear equation in 3 variables is of the form ax plus by plus cz equals d. So here a, b, and c are real numbers, also d as well. But it's important that a, b, and c are not all 0 at the same time, because then all of the variables would disappear. So we want to think about these things as planes in space. So when we have a linear equation with only 2 variables with x and y, we have a line that's drawn on a 2-dimensional plane. Think about a line that you can draw on a sheet of paper. When we have an equation with 3 variables, x, y, and z, we're looking at 3 dimensions. So we can go vertically, horizontally, and then we have depth. Think about like coming out of the chalkboard or out of the sheet of paper. So here we're thinking about a plane, which is a flat 2-dimensional surface that lives in a 3-dimensional space. So imagine a sheet of paper that goes on infinitely. So a solution to a linear equation with 3 variables is what we call an ordered triple that has x, y, and z. So any ordered triple x, y, z that makes that one equation true is considered a solution. Now we're going to be looking at solving a system of 3 equations with 3 variables. So we're talking about taking 3 planes and intersecting them. We're looking for that intersection point. So here's what we are trying to find. So here's a picture of 3 planes, right? So this is a 2-dimensional image of a 3-dimensional object. So there are 3 planes here. So one is orange, we have a light blue, and then we have like a darker blue here. So these 3 planes would be infinite, so that they have some edges here because we have to draw them on a image, but they are infinite. They go on in either direction forever and ever. These 3 planes intersect at one point labeled P in the picture. That one point is located by an ordered triple, x, y, z. So we're trying to find this one point. So we're going to go through a system of elimination, like we do with 2 equations with 2 variables, and we're going to eliminate one of the variables and eliminate another to find one solution, and then work our way back to get the other variables. And we're hoping that we get this one point as our solution. But just like when we have 2 equations with 2 variables, that doesn't always happen. So here's one of the cases where we would have no solutions. In this case, all 3 planes are parallel to one another, so they don't ever intersect at all. This would be considered an inconsistent system. There are no solutions, no points that sit on all 3 planes at the same time. Here's another case of no solutions, where 2 of the planes are parallel, the light blue and the dark blue here, and then the other plane intersects them at some angle, but again, there are no points in common for all 3 planes at the same time. There are points in common for 2 of the planes, but not all 3 of them. So there is no solution to the system of 3 equations. Here's another case where we have no solution. So all 3 of the planes intersect the other 2, but they don't all 3 intersect at the same time. So there is not one point that sits on all 3 planes at the same time, so there are no solutions to the system. Now we will also see cases where we have infinitely many solutions. Here's one picture of how that might occur. So the 3 planes intersect kind of like in a pinwheel fashion, where the intersection is not just one point, but a line. So that line would have to be described given the coordinates x, y, and z. But there are infinitely many points on that line, and every single one of those points would live on all 3 of those planes at the same time. And of course, this is what we call a consistent system because there is a solution, but we have dependent equations because there are more than one. Here's another case of infinitely many solutions. It is possible that 2 of the planes coincide with each other. So the light blue and the dark blue are actually the same plane here, modeled by 2 different looking equations but are essentially the same, and then the other plane intersects them at some point, and then again we have infinitely many solutions because that intersection is a line, not just one point. And finally, all three planes could coincide, so the orange, the light blue, and the dark blue are actually the same plane in this picture, so they would intersect at every single point that's contained on either of those planes. So we would have still infinitely many solutions, but these solutions would be described in the equation with three variables because there is a plane of those solutions. Alright, so we're going to solve these algebraically. There are other methods that can be used to solve a system of three equations and three variables, or any number of equations with any number of variables. But we're looking at a simple algebraic solution using the elimination method, very similar to what we did when we had two equations with two variables. So what we're going to do is take two of the equations. We're going to decide on a variable to eliminate, and you have to decide for yourself which is the easiest variable to eliminate. Then you're going to choose a second pair of equations and eliminate the same variable. So if you eliminated x with the first two equations, then you need to eliminate x with the second pair of equations. That'll bring you down to a 2x2 system. So a 2x2 system means two equations, two variables. This is just like we've seen before, so you can solve that using elimination again, or if you like the substitution method, you could use that method. After we find those two variables, whatever they are, we're going to go back to one of the original equations and find that last remaining third variable. Alright, so we're going to look at 4 different examples. The first 2 will fit into this video, but the third and the fourth will have it in a separate video. So let's take a look at the first example here. We have 3 equations with 3 variables, x, y, and z. Alright, so I have the 3 equations written out here. And what I like to do is go ahead and label the 3 equations with Roman numerals just to help me keep track of everything. Oops, let me go back to that. So what we want to do is take 2 of the equations and eliminate the same variable. So I'm going to start with the first and the second equation, excuse me, the first and the third equation, and I'm going to eliminate the variable y. And I chose that because if you notice, the y's are opposite in sign, so I could easily eliminate the y by just adding those 2 equations together. So my plan again is to take the first and the third equation and eliminate the variable y. So here I am just rewriting each of those equations. And labeling is so important here, so this is the time to take some space to write it out, to keep track of your work, because you could easily make a quick human type error, like not copying down something correctly or not reading your own handwriting properly and making a big mistake. So here I'm just adding the 2 equations together, the y's cancel. So I'm left with the equation 7x minus 4z equals 2. So this is a new equation that I have not seen before, so I'm going to give it another label, number 4. Now I need to take a second pair of equations and eliminate the same variable y. I have to use the second equation because I haven't used it yet. But here I'm going to pair up the first and the second equation, but still eliminate y. So it's very important that I eliminate the same variable. Here I am rewriting. And you'll notice here that the y's aren't going to eliminate right away because the coefficients for y are not opposites. So I have to multiply the first equation by positive 3 so that the coefficient for y is opposite and that will cancel out. Make sure that when you are multiplying that you multiply everything in that equation by 3. The second equation is going to stay the same. And let me go ahead and add those two together. So this is a new equation that I have not yet seen. So I'm going to go ahead and label this equation number 5. So now I have two new equations, 4 and 5, and I'm going to take these two new equations, oops, go back. Okay, so I'm going to take my two new equations, 4 and 5, and I'm going to form a 2x2 system with these two equations. And then I can go ahead and just solve this system just like I would before. So I get to decide now, do I want to eliminate x or do I want to eliminate y? Oh, excuse me, z. And in this case, I decided to eliminate z. And that means I'll multiply the top equation by positive 5 and the bottom equation by negative 4. I'm multiplying the bottom equation by a negative because that will change the sign of the coefficient. So now equation 4 is 35x minus 20z equals 10. And the fifth equation, negative 44x plus 20z equals negative 28. Okay, so I'm going to add these two equations together. The z's will cancel out here. And I could go ahead and solve for x. I have negative 9x is equal to negative 18 dividing by negative 9 on both sides. And that gives me x is equal to 2. Alright, so now I could use that x to go back and find the z from the system up here. So I could use either equation 4 or equation 5 to find z. I chose equation 4, just rewriting the equation. I'm going to substitute in the value of x, which is positive 2, and then go ahead and find the corresponding value for z. So here I'm just solving just like I normally would. One equation, one variable, just isolate that variable. And I have z is equal to positive 3. So far we have two variables. We have x and we have z, so we need to go back and find y. So we need to find one of the original equations that contain x, y, and z. You can choose any three of those equations. I chose the first one. I'm going to substitute in the value of x that I have and the value of z, and then solve for y. So I'm combining like terms that are on the same side first. 6 minus 3 is 3. And then subtract 3 from both sides. Right, so now I have y. I have all three variables, x, y, and z. I'm just going to write them as an ordered triple. So make sure you put them alphabetically, x, y, and z, in parentheses with commas in between. Right, so it looks like we are low on time for the second example, so I'll put all three of the examples here, starting with number 2, 3, and then 4 in the next video. Stay tuned.